Hi everyone. So Ilyana and I worked with Dr. Walk last summer in for math department, and we worked on a research called Games of Best Choice, the hiring problem among the games of best choice.
Okay, so the secretary problem or the hiring problem was first published in 1960 by Martin Gardner in the Scientific American. This was posed as kind of a riddle or problem, and it came with 6 features. The problem to solve was that there's one interviewer and they want to hire the very best person to be their secretary or whatever to fill the spot. These 6 features include that there's only one position available. There is a given number of applicants called N. These applicants are then interviewed in a random order, and the interviewer can rank them as they are interviewed. However, they have to accept or reject the interviewee right then and there. They cannot recall them. And then success is defined as hiring the very best applicant in this original problem. The example here is called the optimal stopping problem, but variations include the dating or marriage problem, where someone doesn't know how many applicants there are and they want to find the very best applicant to marry, in a sense.
So somebody solved this problem, and the known optimal solution is called 37%. So in this strategy, I will interview, let's say I'm a hiring manager, and I will interview the first 37% of applicants and reject them. And the reason why I'm rejecting them is because I have no information about the applicants. I don't know what kind of skills they have. So they will be my training set. After rejecting those 37% of the applicants, first 37% of the applicants, I will choose the next candidate who is better than all earlier candidates. And this strategy succeeds 37% of the time as n approaches to infinity. In other words, if I use the strategy, I have 30% chance that I will win this game. So here's an example. If I have 51 people applied for this position, 37% of 51 is 18, approximately 19. So if I'm using the strategy, I'm going to interview the first 19 applicants and they're going to be my training set. So I will reject them. And let's say Dr. Walk was one of the best applicants in the 19 applicants. So my job or my goal is to find the person who is better than Dr. Walk.
Okay, so something that was originally said in the 6 features was that the interviewer can rank the applicants as they are seen in comparison to the previous applicants. And this is called relative ranking. So one thing to know about relative ranking is that the best candidate is shown as the highest number. This may seem a little bit backwards, but it makes sense later on. So say that the first applicant comes in, they are obviously just going to be number 1. There's nothing to compare them to. If the next applicant comes in and is worse than the first applicant, this would be portrayed as 2-1. Then the next applicant comes in and is better than both the previous, it would be 2-1-3. And if the final applicant comes in and is worse than the first and the last, but is better than the second, it would be 3-1-4-2. And then here is an example of an n equals 3. So there's 3 applicants of the relative ranking tree that you would see with them. So as you can see, it goes by factorials. So there is 6 permutations here to be seen, showing all of the different rankings that could happen if there are 3 candidates that come in. And here is the n equals 4 relative ranking tree. So you can see the blue highlighted path is an example that could be taken if the very best candidate was right away. It ends up being 4 right at the very first number, and then the worst candidate would be 1 in the second position, and so on and so on.
So another concept that we looked at was probabilities of success. So we called this state probability and go probability. State probability is probability of success if we stay on the current candidate and hire the current candidate. So they will be marked in red. Go probability is probability of success if we reject the current candidate and go on exploring other candidates. And those probabilities will be in green. And during our research, we found the state probability formula, and it turned out to be a very simple formula. So N would be number of candidates, I would be current candidate, and we can just plug those numbers to find out the state probability. And here's the relative ranking tree with stay and go probabilities for n equals to 3 if we have 3 candidates. And as you can see, this is an example. So 1/3, if we decide to stay, we're gonna have 2/3 probability of winning because this 2, the second candidate is the best. If we decide to go and explore other candidates, the last person would be the best candidate in just one occasion. And as Ileana said, it increases factorially, and we have like as n increases from 3 to 4, we're gonna have 24 different permutations. So it gets more and more complicated.
Next, we started looking at variations on the original 6 features of the published secretary problem. So pattern avoiding is the variation on the interviewer interviewing in a random order. So instead, now the interviewer has prior knowledge of what the order will be. This could be an example of they have a resume, they know about about how they're going to fit in, but maybe not the total answer of how they're going to fit. But this would be a way to weed out the orders that mean that you're going to be interviewing the worst person after the best person. So this would be in a 2-3-1 pattern. You would see 1 is the worst person. So why would you interview them after interviewing 3, the best person? So here you can see a relative ranking tree with the 2-3-1 pattern avoiding crossed off. So that takes out the 2-3-1 branch and all of the 4 permutations that come off of that. But it also takes off some of the other branches permutations because of the way that they are written. So like 3-4-2 would also be an example of interviewing a worst candidate after a best candidate. Or 2-4-1 is another example of that. So once you take out all of the permutations that have 2-3-1 patterns, you are left with a tree that looks like this, and you can figure out stay and go probabilities in this kind of tree as well.
So as Eliana talked about classic version of the secretary problem, applicants are uniformly distributed, so it's going to be random. The order they will be interviewed is going to be random. But if they are aware of the 37% strategy that I am or the hiring manager is using, there is incentive to not be in the first 37% candidates who's going to be interviewed. However, in some permutations prove to be incentive compatible, which means both the stay and go probabilities are equivalent in all non-zero branches. So there's no advantage to be in certain position to be interviewed for the candidates. As we looked at the avoiding patterns, both 1-3-2 and 231 avoiding trees are incentive compatible. So here's the tree, and let's say this branch has 0, so we're not going to look at this. We're going to ignore this and look at the non-zero branch. And state probability is 2/5, and go probability is also 2/5. And it follows this same pattern in all non-zero branches.
We also explored a couple of other things, such as the go probability equation, higher candidate numbers, and top T candidates. So with the go probability equation, we were able to find a recursive equation, but we were not able to find a non-recursive equation. So without knowing what you previously had and running all the way up until whatever number you were looking for, there was no way to find that equation given the time that we had this summer. We also looked at higher candidate numbers. Being that they do get so big so fast, it's hard to do them by hand. So we started using Python and coding a way for it to give us the relative ranking trees for the bigger numbers. We started at n equals 6, 7, and so on. And then finally, we looked at top T candidates. So this includes a variation on the 6 features of looking at you would qualify success as not just the very best, but maybe any of the 3 best. You'd be okay with any of the 3 best or the top 2 best, whatever you define T as. So we looked at how this changes incentive compatibility, stay and go probabilities, etc. There are lots and lots of variations that can be done with this problem, and there's a lot more research that can be done. We just got started this summer, so we didn't get too far into a lot of these things, but there's a lot of exploration that can be done. Thank you very much.